Essential discontinuity. So we have two types of discontinuity. I am flashing again our definition of continuity. A function is continuous at a point x is equal to a if the following conditions are met. F of a exists, or f of a is defined. The limit of your function as x approaches a exists, and it is equal to f of a. So if any one of those is not met, you will have a discontinuity at the point x is equal to a. But we have two types of discontinuity: a removable discontinuity and an essential discontinuity. In your removable discontinuity, what you have is a case in which the limit of your function as x approaches a exists, but it becomes discontinuous either because f of a does not exist, or f of a is undefined, or maybe it is defined, but the limit of our function as x approaches a is not equal to f of a. An essential discontinuity is a function where the limit does not exist as x approaches a. So basically what it is telling you is that there is nothing that you can do about the point of discontinuity. It is essential, it will remain discontinuous at that point. So a function has an essential discontinuity at a point x is equal to a when the limit of your function as x approaches a does not exist. And it can happen in two ways. Either the discontinuity is a jump discontinuity, or it is asymptotic discontinuity. Okay, so what I'm going to do is I'm going to flash to you functions, their graphs. One is removable and one is an essential discontinuity. So this one would have a removable discontinuity when x is equal to 1. Why so? Because the limit exists. As x approaches 1, the limit of our function is equal to 1. This one is discontinuous when x is equal to 1 because the one-sided limits are not equal. When x approaches 1 from the left, the value of your function approaches 1. But when x approaches 1 from the right, the value of your function approaches 2. So the one-sided limits are not equal. So this is an example of a jump discontinuity. So why do you call it jump discontinuity? Because if you are to graph this function, okay, when you reach this point, you have to jump to that point to continue the graph. So this is an essential discontinuity, and in particular, it is a jump discontinuity. So this one is showing to you a removable discontinuity when x is equal to 0, because f of 0 does not exist. But the limit of your function as x approaches 0 from the right is equal to the limit of your function as x approaches 0 from the left. So this means the limit exists as x approaches 0, and it is equal to 0. So this one is a removable discontinuity. This one has an essential discontinuity. When x approaches -3 from the left, your function goes to infinity. When x approaches -3 from the right, your function approaches infinity. And so when that is what you are seeing in the behavior of your function, your conclusion is the limit does not exist. Because in order for the limit to exist, it must be equal to a finite real number. Okay? And so I think you can now tell why this is called an asymptotic discontinuity. Because your function is approaching a vertical asymptote. Okay? Example 1.39, recognizing jump discontinuities. Well, it is easy to see the jump discontinuity if you see it as a graph. So again, the reason why you call it jump is because when we are graphing the function, we cannot graph it without lifting our pen from the paper. We have to jump. Sometimes the function is not given to us in the form of a graph. It is defined to us, let's say for example in this way. It is defined in the form of a piecewise function. So when you have something like this, right away, you will look at where your domain is divided into two intervals. So here, the division in the intervals happen when x is equal to 1. So right away, this one is a candidate for a point where your function might be discontinuous. Because if you were to look at this is a polynomial function. It is continuous for all real numbers less than 1. This one is also a polynomial function. And polynomial functions are continuous in its interval. So it's going to be continuous for all x's greater than 1. So our point of interest now is at this point when x is equal to 1. So what do we do? What we do is we evaluate, does f of 1 exist? Well, yes, it is equal to, look at that. It is equal to 1 plus 1, it is equal to 2. How about the limit? When x approaches 1 from the left, so that means your x's are all less than 1, the limit of your function is 1 plus 1, it's equal to 2. How about when x approaches 1 from the right? So your x's are greater than 1. So when x approaches 1 from the right, this becomes 1. 1 minus 3 is negative 2. Negative 2 squared is 4. So the one-sided limits are not equal. Conclusion, it is discontinuous at 1. What type of discontinuity? It is an essential discontinuity because the limit does not exist. And in particular, it is a jump discontinuity. So this is the graph of this function. It is a jump discontinuity. So we will sketch this part of the graph. But when we get to 1, to continue the graph, we have to jump there, okay, and continue the graph. Recognizing asymptotic discontinuities. The key word here is asymptotic. It has to do with the vertical asymptotes. And you know why they are called vertical asymptotes, and you know how the graph behaves in relation to the vertical asymptotes. The limit of your function either goes to infinity or negative infinity, in which case the limit does not exist. Consider the function defined by f of x is equal to x over x squared minus 4. Find where it is discontinuous. What is the type of discontinuity? So right away you can say that this function is not continuous when x is equal to 2 or when x is equal to negative 2 because your function is undefined. Your function does not exist when x is equal to 2 or negative 2. So this is the graph of the function defined by f of x is equal to x divided by x squared minus 4. These are the vertical asymptotes. As x approaches negative 2 from the left, your function goes to negative infinity. When x approaches negative 2 from the right, your function goes to positive infinity. When x approaches 2 from the left, your function goes to negative infinity. When your x approaches 2 from the right, your function goes to positive infinity.